In computational complexity theory, the complexity class EXPTIME is the set of all decision problems that have exponential runtime, i.e., that are solvable by a deterministic Turing machine in O time, where p is a polynomial function of n. In terms of DTIME, we know PNP, PSPACE, EXPTIME, NEXPTIME, EXPSPACE, and also, by the time hierarchy theorem and the space hierarchy theorem, that PEXPTIME and NPNEXPTIME and PSPACE, EXPSPACE, so at least one of the first three inclusions and at least one of the last three inclusions must be proper, but it is not known which ones are. Most experts believe all the inclusions are proper. It's also known that if p equals np, then EXPTIME equals NEXPTIME, the class of problems solvable in exponential time by a non-deterministic Turing machine. More precisely, EXPTIME NEXPTIME if and only if there exist sparse languages in NP that are not in P. EXPTIME can also be reformulated as the space class PSPACE, the problems that can be solved by an alternating Turing machine in polynomial space. This is one way to see that PSPACE EXPTIME, since an alternating Turing machine is at least as powerful as a deterministic Turing machine. EXPTIME is one class in an exponential hierarchy of complexity classes with increasingly more complex oracles or quantifier alternations. The class 2 EXPTIME is defined similarly to EXPTIME but with a doubly exponential time bound. This can be generalized to higher and higher time bounds. EXPTIME complete. A decision problem is EXPTIME complete if it is in EXPTIME, and every problem in EXPTIME has a polynomial time any-one reduction to it. In other words, there is a polynomial time algorithm that transforms instances of one to instances of the other with the same answer. Problems that are EXPTIME complete might be thought of as the hardest problems in EXPTIME. Notice that although we don't know if NP is equal to P or not, we do know that EXPTIME complete problems are not in P. It has been proven that these problems cannot be solved in polynomial time by the time hierarchy theorem. Other examples of EXPTIME complete problems include the problem of evaluating a position in generalized chess, checkers, or Go. These games have a chance of being EXPTIME complete because games can last for a number of moves that is exponential in the size of the board. In the Go example, the Japanese Go rule is sufficiently intractable to imply EXPTIME completeness, but it is not known if the more tractable American or Chinese rules for the game are EXPTIME complete. By contrast, generalized games that can last for a number of moves that is polynomial in the size of the board are often PSPACE complete. The same is true of exponentially long games in which non-repetition is automatic. Another set of important EXPTIME complete problems relates to succinct circuits. Succinct circuits are simple machines used to describe some graphs in exponentially less space. They accept two vertex numbers as input and output whether there is an edge between them. For many natural P-complete graph problems, where the graph is expressed in a natural representation such as an adjacency matrix, solving the same problem on a succinct circuit representation is EXPTIME complete, because the input is exponentially smaller, but this requires non-trivial proof, since succinct circuits can only describe a subclass of graphs.